بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. ما زلنا مع سلسلة النسبية العامة وعلم الكونيات الجزء الثاني، علم الكونيات الكمية مقارنة بنظريات على يوسف. وها هي الحلقة التاسعة بعنوان أن جيم هارتل، البروفيسور جيم هارتل، يؤكد على النسبية العامة لتفسير المستقبل كما تنبأت نظريتي. ما سنشاهده في هذا الفيديو أن جيم هارتل يحاول أن يفسر تطور الكون من خلال ما يسمى بالكوانتم جرافيتي. وتم تطوير في الفيديو السابق كما رأينا أنه تم تطوير ما يسمى بنو باوندري ويف فانكشن، واضطر العلماء أن يستخدموا ما يسمى ب سيمي كلاسيكال ابروكسيميشن حتى يستطيعوا أن يتعاملوا مع الفضاء الكلاسيكي. في هذا الفيديو سيكمل جيم هارتل ما انتهى إليه في الفيديو السابق، وسيخبرنا أن من أجل تطور هذه النظرية لابد أنه في المستقبل يكون هناك سيطرة كبيرة للنسبية العامة في تفسير سلوك الكون وتركيبه. وهذا ما ذكرته نظريتي في هذا الأمر، وبالتالي يكون هناك شيء من التفسير للكوانتم جرافيتي سيكون في كفة النسبية العامة، أو سيكون مائلا في كفة النسبية العامة. تعالوا نشوف الفيديو ونحاول أن نعلق عليه.
Invariant, as all our best candidates are, then to explain the arrow of time, I have to say something about the quantum state. The CMB, the large-scale structure I've already mentioned, the existence of isolated systems. We're all semi-isolated systems in this room, but that's not guaranteed in the theory in any sense. It's a property of, and there were none in the very early universe. They emerged. The topology of space-time, right? Whether it might be, for example, something like a torus or a hall of mirrors or something like that, or an iosphere. The number of large and small dimensions in a theory that has those, the number of time dimensions, for example, coupling constants of effective theories. There's a huge list of things we might hope to get out of the state, and I'm going to report very briefly. So to do that, I'm going to give you a very quick introduction to wave functions of the universe, which represent quantum states, in a very simple class of models. Models which are homogeneous and isotropic, and therefore have, there we go. All right, therefore have only one quantity, which is, so they're like spheres, and A, for example, is a scale factor that represents the overall size of the universe at any one time. Now, in ordinary quantum mechanics, wave functions are functions of x and t, and you can think of those as the quantities. If you have a history, x of t, they tell you what, they specify the history on one space-like surface. In quantum gravity, we also have histories. Here's, for example, a history of the expansion of an expanding and collapsing universe, described by the scale factor A, which is a function of time. And if we have a scalar field in addition to the geometry, it's usually argued that the wave, you don't need an additional time variable, right, to label what point you are, because the size of the universe itself tells you where you are in this curve. So wave functions in a very simple model will be a function of scale factor and one field, let's say, for example, scalar field. It's important to stress that wave functions of the universe are not an initial condition. because initial and final already presume that you have a notion of space-time, and we're seeking to produce the notion of classical space-time. So you have to think of them in four-dimensional senses as representing something that will tell you what went on in a four-dimensional way, what went on then, what goes on now, and what will go on in the future. And that way it becomes predictive. Now I'm going to report on one particular state, right, which is Hawking's no boundary of the wave function of the universe, only because that's been the most developed. This wave function is the analog for closed cosmologies, right, of the ground state in ordinary field theory. And since there's plenty of evidence, the ground states typically are very simple, and the early universe was very simple, more homogeneous, more isotropic, more nearly in thermal equilibrium, that might be a good candidate for the quantum state. It's theoretically based and, you know, in a rough connection with observations. But you can't, in a closed cosmology, think of a ground state as being the lowest eigenfunction of some Hamiltonian, because from the diffeomorphism invariance of general relativity, the closed cosmology, the Hamiltonian vanishes identically. Also, everything is an eigenstate of it. But in ordinary field theory, there is another way of constructing the bound state by a Euclidean sum over all histories that match the arguments of the wave function. And so we can construct a state which is the Euclidean sum over all four-dimensional geometries that have one boundary, right, where the arguments of the wave function, this is supposed to be a four-dimensional geometry, scale factor, four-dimensional scalar field, matching a three geometry and a three-dimensional scalar field, and we just do an integral over e to the minus the action of the theory, and we produce a wave function which is the analog of the ground state, and that is the candidate I'll discuss for a wave function of the universe. So first of all, how do we predict that there's any classical space-time at all? This integral, which I showed you on the previous slide, imagine it doing by steepest ascents. Then you basically, the result will get e to the minus times the extrema of the action. And the no boundary wave function therefore predicts something like this. Since the extrema are generally complex, I've tried to draw a picture of one here, right? Here's the one boundary where the wave function is defined, and that's the no other boundary. And this is complex. We call them fuzzy instantons, but there's no particular reason for that. At any rate, the state would have this form, and it will have a real part and an imaginary part to the action. But that should look familiar to you. It's ordinary WKB. And so we predict an ensemble of classical spacetimes, which are the integral curves of the imaginary part of the action here. That is, the solutions to the Hamilton-Jacobi equations, momenta equals the gradient of S, and the probability is roughly.
هنا أريد أن أؤكد مرة أخرى على يعني توفيق الله سبحانه وتعالى لي عندما تبنيت نظرية WKB. وأنا لم أكن أعلم في الحقيقة أن يعني كوانتم كوسمولوجي أو استخدام ميكانيكا الكم داخل علم الكونيات سيكون في حوجة ماسة لنظرية WKB. WKB تخبرنا بأشياء أكبر مما يتحدث عنها جمع هارتل الآن. تتحدث عن أشياء كثر في قوانين التناظر وتركيب قوانين تناظر أخرى يعني في داخل هذا الكون بطريقة عجيبة جدا جدا، وتتحدث عن connection field، وتتحدث يعني تجدون هذا الأمر في كتاب الحلقة 50، وتجدونها أيضا في فيديو عن الكوفارينت برينسيبل أو الكوفارينت ديريفيتيف برينسيبل. فهو توفيق من الله سبحانه وتعالى أنني تبنيت هذه النظرية التي يمكن أن تفسر الكون والكون هو أقرب إلى الكلاسيكي من الكوانتمي. هذا الشيء واضح جدا وجلي جدا. في الحقيقة ال WKB هي ليست فكرة أصلية، يعني السبب الذي جعلنا نتنبأ وأتبنى WKB هي كتبي أو السرياك أو نظرية السرياك اللي هو النسبية الخاصة في المراجع المتسارعة، أعطتني نتائج مثل WKB، وهذا سبب أنني يعني تبني لل WKB. فال WKB جاءت مكملة للسرياك، فالتوفيق الإلهي الحقيقي هو في تبني السرياك وليس WKB، لكن WKB جاءت مكملة للسرياك. الحمد لله.
Square of the wave function, which is e to the minus 2IR. So thus we've predicted an ensemble of possible classical spacetimes for what the universe might be like, with probabilities for what they are. And not all classical spacetimes are predicted. Whoops. So let's just give one simple example. Ask the question, does the no-boundary wave function predict high probabilities for inflation in the early universe? The answer is no, it does not. By itself, it predicts all early histories inflate, but the probability for the number of e-folds, roughly here, is declining. But in cosmology, you have to take into effect that everything is inside, including us as observers, which are also quantum mechanical systems in the universe. So the theory may predict probabilities for what occurs, but it's a different set of probabilities for what we would observe, because we're particular systems and we only have a probability to exist in any one Hubble volume. It's more probable that we exist in larger universes because there are more places for us to be predicted. And that means that even though the probability for inflation to occur with a large number of e-folds is small, the probabilities for us to observe a lot of inflation by our observations is actually high. Thus, the theory agrees with the experiment. Well, that's homogeneous and isotropic. Of course, it's standard perturbation theory to extend that by considering little fluctuations, right? That's a typical graduate student problem. We did the homogeneous isotropic part. Now you can expand in fluctuations and calculate that. Since the no-boundary wave function is essentially a Euclidean construction, right, it won't surprise you that the fluctuations start essentially in their ground state, something called the Bunch-Davis vacuum. And if you know the technology of that, where these are the standard slow roll parameters, and these are the size of the fluctuations, they give you the standard prediction that's usually assumed in cosmology to explain the scale-free invariant spectrum or something that we see in large scales. So this works pretty well also. In short, the wave function predicts probabilities for different CMB maps, as we saw in the different, as in the preceding talk. Arrows of time. Well, our universe exhibits a number of arrows of time. So there's the fluctuation arrow. The fluctuations seem to be small in the beginning and grow as it goes on. There's the thermodynamic arrow, the growth of entropy, right, in the universe. The radiation arrow, the retardation of electromagnetic radiation, and the psychological arrow that we order prediction into past, present, and future. These arrows are all, I don't have time to go into it, but they're all essentially the same. They follow from the fluctuation arrow. And they can be explained by this special quantum state, like the no-boundary wave function, where the dynamical laws are time symmetric, right? But the state of the fields is different in different geometries. So, no-boundary wave functions vanish at one and only one place on the instanton, down here from symmetry. This means the fluctuations, turns out to mean the fluctuations are small at only at one place in the universe, which is, if we only have an expanding universe, would be at the beginning. But an interesting example is, what if we have a bouncing universe, right, that contracts and then re-expands? It turns out the fluctuations are not small at one end, large N, or the other, they're small in the middle. That means the arrow of times, all the arrows of time, will point in opposite direction on opposite sides of the bounce in a symmetric way, right? Even though there's an arrow in each place. That's not very good for getting observational information about the other side of the bounce, because people back here will have had about as much chance of sending us information as we have sending information backward in time to tell people not to vote a certain way in an election. It's not going to be done. Well, I had a big list there, which I'll go over again, but there are some of the successes, but there are some things that are interesting that we just haven't been able to do yet. A space-time, geometrically or mathematically, is a manifold with a metric on it. A manifold is just the topological structure of the geometry. So, for example, you can imagine manifolds like a sphere, or have a handle on them, as in these fanciful pictures on the side, or like a donut and so forth. If we seek to predict the classical metric, we might also seek to predict probabilities for what manifolds we have. And that has an observable effect if it's not on too large a scale. That is, imagine, for example, the universe was like a torus, or one of these halls of mirrors you see, where you see infinite reflections going off in different directions. That would have an effect on distorting the CMB that we observe, because you'd see one reflection of it, another reflection of it, another reflection of it, if it wasn't on too huge a scale. So large-scale topology, at some level, is detectable by its effects on the CMB, and that's been looked for, and so far there are no effects. But it's a very hard problem to do, because I showed you how saddle points led to a very simple universe, but we have very little information about what kind of saddle points, complex saddle points, would exist on manifolds with complex topology. But if we had them, then we could actually compute. So, where are we on our scorecard? The features we might expect to be predicted, or here's the list I had in the beginning. Classical spacetime, yes, the theory does predict that the spacetime is classical, and moreover, what the classical spacetimes on very large scales are. Early homogeneity and isotropy with inflation, yes, it predicts that through the fluctuations. Fluctuations start in their ground state, yes. Arrows of time, it certainly predicts the arrows of time as a special state in a time-symmetric theoretical framework. The CMB large-scale structure, there are a lot of things I didn't say here. Isolated systems, for example, the separation of the Planck scale, the remarkable and very lucky fact that we didn't have to know anything about quantum gravity to do the rest of physics, right? We only have to know about it in extreme circumstances. Topology of space-time, number of large and small dimensions in principal predictor, etc. So, some successes, I've only been able to report on a few. That's quantum cosmology. But in this centenary year, it's maybe appropriate to think about general relativity in a broader context. Robert Oppenheimer, writing a eulogy in Reviews of Modern Physics, I think in 1956, right after Einstein's death, was kind of critical of general relativity. He said, in the 40 years that have elapsed since the classic initial test, what he means, these have remained, the deflection of light, the precession of the perihelion, the gravitational redshift, and so forth. These have remained the principal, and with one exception, the only connection between general relativity and experience. I think the implication is that the theory had been, in some sense, a failure. And indeed, if you plot, make a plot, a convenient plot that I learned from Clifford Will, of the mass of objects measured in grams going up this way. I apologize for the low quality of the graphics here. Versus
انظر إلى هذه المعادلة الغريبة جي ام على ار سي تربيع. ماذا تذكركم بمعادلة الطاقة، الدالة الأسية في معادلة الطاقة. وهذا هو شيء مهم جدا جدا، أن الدالة الأسية تلعب دور، وهذا ما ذكرته في الفيديو السابق، أن الدالة الأسية تلعب دور كبير في تسطيح الكون. وفي الحقيقة يعني لابد أن يكون هذا الاتفاق، هذا مسار الاتفاق، لأنه بالتحليل العميق لتطور الكون لابد أن يكون هناك تأثير قوي جدا جدا للدالة الأسية موجودة في إحدى المعادلات. أي معادلات؟ الحمد لله شكر لله. الخط المستقيم هذا في الرسم البياني يخبرنا بتأثير الدالة الأسية كما تنبأت نظريتي بالضبط. ارجعوا للفيديو السابق لهذا مباشرة. كما تنبأت نظريتي بالضبط أن الدالة الأسية هي سبب تسطيح الكون وليس الطاقة الصفرية. طيب تعالوا نواصل.
their size in centimeters, then roughly speaking, relativity is important when the ratio gm over rc squared is approximately 1. That is lying along this line here. Can't be bigger than 1 because you're inside black holes, but the further phenomena are closer to the line, then the more relativistic effects are important. So the present universe, in some approximate way, runs along this line from the Planck scale way down here all the way up to the present. And the sun, no, it's an order 10 to the minus fifth effect, is somewhat close to the line, and that's the way it looked in 1956. Oops. Yeah. Today, it looks better astrophysically. There are a lot of things. There's the quantum gravity scale down here, the end of inflation. So, we have pretty good evidence for some sort of inflation occurring. Primordial black hole evaporating today, which we haven't seen yet in the diffuse X-ray background. And many more tests of the theory of relativity on solar system scales, remarkably accurate one, for example, the test of the bending or the Shapiro time delay by the Cassini mission to a part in 10 to the 5th. That was unheard of, certainly. Neutron stars, properties of neutron stars, maximum masses, and so forth. The global positioning system, as Cliff stressed for you the other day, would fail in a half an hour if it didn't compensate for the effects of general relativity. Black holes and galaxies we have, and of course there's the present universe. So it's much better today. But if you're interested not in just what's going on today, but where did all this stuff come from, right? Then GR, first of all, is the key, as I've already mentioned, to the existence of the quasi-classical realm, to the utility of classical physics, and it's central to the origin and properties of today's isolated systems. So if you're working in a laboratory and you trace back, right, where we are, you're talking about a curve that started out here from the Planck scale, came up, then the fluctuations grew under the action of the quantum fluctuations grew under the action of gravitational attraction to collapse, eventually to make galaxies, stars, planets, very small fluctuations, us, and doing experiments in laboratories. So if you're interested at all in history, you're interested in general relativity, both
مرة أخرى الفلكشويشن تتناسب مع الجاذبية، وهذا ما افترضته مرارا وتكرارا، ذكرته مرارا وتكرارا في جميع فيديوهاتي السابقة وكتبي السابقة، أن الفلكشويشنز هي تأثير مباشر للجاذبية، وبدون الجاذبية سيكون من الصعوبة إنتاج الأزواج، ومن صعوبة نجعل السبيس تايم أو نجعل الفيلد يتذبذب. فالجاذبية والكتلة العالية هي التأثير، هي التي تسبب لنا الفلكشويشنز، تسبب لنا تذبذبات الفيلد، وتسبب لنا ميكانيكا الكم.
Classical and quantum. So in 1956 it looked like this, but in the future it may look more like this. There's increasing evidence that gravity might be, in some sense, a theory of everything, right? Where everything is affected by general relativity, going backward. So a century after its inception, everything is affected by general.
طبعا هنا في شيء مهم جدا. انظر انسايد بلاك هول، هذه المنطقة البيضاء انسايد بلاك هول، هذا شيء فيها شيء غريب جدا، وهو أن عندما ننتقل بالنسبة للملاحظ موجود داخل الثقب الأسود، وينتقل من سطح الثقب الأسود إلى مركز الثقب الأسود، فإنه ينظر إلى الفضاء مثل الفضاء الخارج الثقب الأسود، بس ما عدا اختلاف واحد، هو أنه سيكون مساره ينزل إلى مساره واحد، يعني جيوديسك يكون واحد نحو مركز الثقب الأسود. لكن الفضاء هو قريب من الفضاء الخارج الثقب الأسود، وبالتالي نرى أنه فلكشويشنز تنقص. لهذا نجد أن لا يوجد كتل في هذه المكان. يعني ننظر هنا الشمس وهنا الأرض، يعني في الجانب المظلل بالأصفر، وحتى يعني كل هذه عبارة عن كتل، بسبب الكتل الضعيفة للكتل الكونية الضعيفة. داخل الثقب الأسود كتلة عالية جدا جدا داخل الثقب الأسود، وبالتالي لا يوجد تنبؤات فيها في المستقبل، لا يوجد شيء فيها. ونظرية على يوسف لا تقول ذلك فقط، إنما تقول أن لا يوجد فلكشويشنز، لأنه فلكشويشنز من سطح كتلة الثقب الأسود أو من أفق الحدث وأنت نازل إلى جسم الثقب الأسود، تقل الفلكشويشنز بصورة كبيرة جدا جدا، مثلما أنك من سطح الثقب الأسود وتنطلق إلى الفضاء الخالي من الكتل أيضا تقل الفلكشويشنز. وهذا تنبؤ لنظرية على يوسف داخل الثقب الأسود.
Going backward. So a century after its inception, Einstein's general relativity is central to physics, both on the frontier of the very large and also the frontiers of the very small.
هذا ما أريد أن أقوله، هذا هو عنوان الفيديو. أن النسبية العامة ستسيطر على الكون في المستقبل، من ناحية الكون الضخم والكون الصغير جدا، وهذا ما تنبأت به نظريتي، ولله الحمد.
Martin Seligman, who was president of the American Psychiatric Association, was the subject of a CNN special, and they said to him, well, what we're interested in is the state of American psychiatry today. So, but we had to be short. How would you summarize that in one word? And he said, good. And then they said, well, that's not very informative. How about 2 words? And he said, not good. They said, well, you just contradicted yourself. So how about 3 words? And he said, not good enough. And ladies and gentlemen, if I had to summarize for you in 1 word, 2 words, 3 words, and 4 words, the state of quantum gravity and quantum cosmology today, it would be exactly that. It's good. Amazing progress has been made. A lot of questions that we never asked before have been addressed and are keeping on being addressed. It's not good, right? Because we're quite far from any having definitive resolution. There are a lot of puzzles like black hole evaporation that are confusing. In short, it's good, but it's not yet good enough. Thank you.
إذن هذه هي يعني مستقبل الكون، وهذه هي ميكانيكا الكم داخل الكون. فميكانيكا الكم داخل الكون يجب أن تتخللها فيزياء كلاسيكية، وهذا يعني أن الميكانيكا الكم ليست أساسية على الإطلاق، وإنما هي نابعة ومنبثقة من معادلة أو من نظرية أكثر أساسية، وهي نظرية يوسف. السلام عليكم ورحمة الله وبركاته.